Morning, students, and welcome to this moment's class. Today, we'll be discussing with you elaborately on the topic two-way analysis of variance. In one of our previous classes, we already had discussed on one-way analysis of variance, where we paid attention to only one factor having effect on our response variable. However, when the number of factors that the researcher is interested in an experiment grows beyond one, and then the researcher now is interested in two factors, we no longer talk about one-way ANOVA, we talk about two-way analysis of a variance. And of course, when we talk about a factor in analysis of variance, it is important that we understand it in detail. What we mean by factor here is, for instance, that a researcher is interested in the recovery time of patients that are treated with different headache drugs. In this experiment, the factor there is drug. And this drug has different levels. Levels here refers to different kinds of drugs which we use to treat what headache. The drug could be Fensic, the drug could be Panadol, the drug could be Panadol Extra, the drug could be paracetamol. All these drug types are targeted to cure headache. So the drug which we have here becomes what we call a factor, and these different kinds of drugs now becomes what we call the levels of what of factor. So when the question is asked, how many factors are involved here? Only one factor. How many levels has this factor? 4 levels. Fensic, Panadol, Panadol Extra, and then paracetamol. When a researcher is interested on the recovery time of patients treated with these different levels of this factor drug, the person will be making use of an analysis tool called one-way ANOVA. However, when someone now becomes interested in the recovery time of the patient, but this time around considering the drug and equally considering the amount of rest that is given to the patient, the person is no longer interested in one factor called a drug. The person now becomes interested in two factors: one, the drug, and two, then the level of what of rest. In this aspect now, the person should be talking about what we call two-way analysis of what of a variance. So the major question here becomes, when are we to use two-way analysis of variance? We can only use two-way analysis of variance when there are two factors in the experiment, and each of the factor has at least one levels on one groups. Considering, for instance, the drug had more than two levels or groups, because we talked about the Fensic, we talked about the Panadol, we talked about the Panadol Extra, we talked about the paracetamol. So in this analysis or in this example or illustration, we have 4 levels of what of drug. We can talk about the amount of what of rest, which you could be talking about somebody resting for at least an hour a day, someone resting for at least 2 hours in a day, and someone perhaps resting for at least 3 hours what a day. So the rest equally exists in different what levels: 1 hour, 2 hours, and then 3 hours. That is a scenario where we make use of what we call analysis of what of a two-way analysis of a variance, because two factors are involved. One factor, drug; second factor, what? Rest. Of course, for us to equally go ahead and begin to make use of two-way analysis of variance, there is what we call assumptions. which the data we have at hand must satisfy before we go ahead to make use of what two-way analysis of what variance. So we talk about assumptions of two-way analysis of variance. Assumptions. Talk about assumptions. Talk about assumptions. Assumptions. The number one assumption we have there is what we call the normality assumption. What we call the normality assumption. Normality assumption. Normality assumption. Then number two, we have what we call independence assumption. Independence. Independence assumption. Or we can use the word independent assumption. Independence what? Assumption. Then number three, we have what we call the equality of variance assumption. Equality of variance. Equality of what? Of variance assumption. And then number four, we have what we call sufficient sample size. Sufficient sample size. Sufficient sample size. What do we mean by the first one that talked about normality assumption? The assumption says that the data which we have at hand, upon which we are going to apply the two-way ANOVA, must be normally distributed or approximately normally distributed. That is what an assumption. Number two says independence. That is to say that the observations in each of the level of the factors involved must be what? Must be independent. Equality of variance. The variance of the observations in each of what of the levels are assumed to be what? To be equal. That is, if you are having four levels, for instance, the variance of the observations in these four levels of the factor are assumed to be what? To be equal. And the last one that says was sufficient sample size. It is expected that the sample size that we have is going to be sufficiently what? Large, such that we can have what we call a precise result. That is what we mean by assumption of a two-way ANOVA. So the concern here is, how do we state the hypothesis of two-way ANOVA? Hypothesis of a two-way ANOVA. Permit me to clean all about assumption. We talk about hypothesis of two-way ANOVA. Hypothesis of two-way ANOVA. Talk about what? Hypothesis of two-way ANOVA. Of two-way ANOVA. We often have three different hypotheses when we are talking about two-way analysis of variance. The first hypothesis is concerned with the first factor in the experiment. The second hypothesis is concerned with the second factor in the experiment, while the third hypothesis is concerned with the interaction effects of the two factors involved in the experiment. So what we want to tell our class or our audience is how to state these hypotheses, because there are two ways of stating these hypotheses. The first way, we talk about H subscript 0. When we talk about H subscript 0, we are making reference to null hypothesis. And we write this way, that AI equals what? 0. AI equals 0. For all I equals 1, 2, 3, down to what? To A. That is to say that the ith treatment effect of factor A is equal to 0 for all I ranging from 1 to A. This 1, 2, 3 up to A, they stand for the different levels of factor A. This is the first level, this is the second level, this is the third level, and this is the eighth level. And the null hypothesis is saying that each of these level, its effect is 0, is equal to what? To 0. That is what the null hypothesis is saying. Against the alternative verse, H subscript 1 saying that what? That AI is not equal to what? 0 for at least one group. For at least one group or level. Remember that the null hypothesis has gone ahead to say that the effect of each level on the response variable is what? 0. The alternative is saying that the ith effect is not equal to 0 for at least one level or one group of the factor. That is to say that if the first level its effect happen not to be or to be 0, we are no longer going to agree with the null hypothesis. We are going to agree with the alternate hypothesis that says that at least one of the level its effect is not equal to 0. This is the null and this is the alternate hypothesis for the first level of what? Of the factor. Then we come to the second hypothesis concerning the second factor in the experiment. We say that H subscript 0, talking about the null hypothesis, that B what? I, B subscript I is equals what? 0 for what? I equals 1, 2, 3 down to what? To B. Okay? I prefer to use here that Bj so that now for all j running from 1 to what? To B. By implication, we are saying that the jth effect of the level of factor B is equal to what? 0. For j running from 1 to what? To B. Against the alternative that H subscript 1, that what? B what? J is not equal to what? 0 for at least one group or level. This is the second hypothesis. The third hypothesis now is talking about the interaction effects. That one we are going to put them in sentences rather than now writing them this way. That one is H subscript 0. We now say there is no interaction effects between factor A and B in the experiment. There is no interaction effects between factors A and B in the experiment. Against the alternative hypothesis, H subscript 1, that says that there is interaction effect between factors A and B in the experiment. This is how to state the different hypotheses of two-way ANOVA. This first one concerned with factor A, this second one concerned with factor B, and this third one concerned with the interaction effect of factors A and B. However, there is a different way of presenting these hypotheses. And permit me to clean this one and show you another way of presenting these hypotheses. So I clean this to here. Another way of presenting this hypothesis is to write this way. H subscript 0 then mu1 equals what? Mu2 equals dot 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 equals what? Mu A. Okay? You are saying that the mean of what? Level 1 is equal to the mean of level 2, which is equal to the mean of level 3 down to the mean of what? Of level A. Therefore, there is no statistical significant difference in the mean levels of the different groups involved in what? In the factor. You now say against the alternative H subscript 1 that mu I is not equal to what? Mu what? J. For I not equal to what? J. You are saying that there are at least two groups or two levels in that factor A that their means are not equal. That is what you mean by this alternate hypothesis. Then you come down to this one, you say that the mu1 is equals mu what 2, which is equals down to what? Mu b. Against the alternative that mu what I is not equal to mu what j. For at least I not equal to j. The same thing is what we are saying here. That the mean of the first level of factor B is the same thing with the mean of the second level of factor B down to the mean of the bth what level of factor what B. Against the alternative that at least two of the means of the two levels, at least the means of two levels are not the same. The third hypothesis still remains the way it is. So this is about stating the what? The hypothesis. So you permit me to clean this. And we talk about the different types of the two-way analysis of variance which we have. Because we have two categories of two-way analysis of variance in terms of the interaction effects. We have what we call two-way analysis of variance without interaction and two-way analysis of variance with interaction. So you permit me to clean this. We write about it and talk about it. I already had mentioned that we have two different classes of a two-way analysis of variance. One, we have what we call two-way analysis of variance without interaction. Two-way, ANOVA. ANOVA, without interaction. And then we have number two, two-way ANOVA with interaction. So what do we mean by two-way analysis of variance without interaction? It is simple. If you remember, while we were stating the hypothesis, we had three different types of hypothesis. The third one talked about the interaction effects. In the two-way analysis of variance without interaction, the assumption is that the two factors involved in the experiment do not interact with each other. And as such, the interest is on the independent effects of the two factors involved without interest on the interaction effects. While in the second one, of course, we are interested on the independent effects of the two factors involved and as well as on the interaction effects of the two factors in that experiment. Therefore, stating the hypothesis of the first class of two-way ANOVA here, we are going to skip the third what as hypothesis. But if the interest is for the two-way analysis of variance with interaction, we are going to include the third hypothesis, which talks on the interaction effect of the two factors involved. That is the two class of what of two-way ANOVA, one without interaction and the other one with interaction. We are now going to talk about what are the steps or the procedures of conducting two-way analysis of what of a variance. The steps or the procedures. So you permit me to clean this. We talk about the steps or the procedures. Talk about the steps or the procedures. The steps of carrying out two-way ANOVA. Of carrying out two-way ANOVA. The steps of carrying out a two-way ANOVA. Number one, you present the data for the two-way ANOVA. Presentation of the data for the two-way ANOVA. Presentation. Of the two-way ANOVA data. Two-way ANOVA data. Number two, we talk about from the data, compute the sum of square errors. Compute the sum. What we mean by SS here is sum of square. So compute the sum of square for the factors involved. Including the error sum of square. That is number two. Number three, we talk about determine the degrees of the freedom for the different effects. Determine the degrees of freedom. Degrees of freedom, DF, for the different effects involved. So we are going to talk about degree of freedom for factor A, degree of freedom for factor B, degree of freedom for what? For error. If we are not paying attention to interaction. But if we are paying attention to interaction, we talk about the degree of freedom for factor A, degree of freedom for factor B, degree of freedom for the interaction of what effect, degree of freedom for error, and then the degree of freedom for total. Then number four, we say compute the mean square. Compute the mean square. When we write MS, what we are talking about is what? The mean square. For the factors involved, or for the different effects. For the different effects involved. Then number five, we now say compute the F ratio. Compute the F ratio. Compute the F ratio. F ratio. Compute the F ratio. Then the last step, which is number 6, will now ask you to compare the F calculated from the data with the F tabulated in the table. Compare the F calculated with the F tabulated in the table. So this is what we are going to do. We are going to follow each of the steps one after the other. First of all, we are going to learn how to present the data for the two-way ANOVA. We now learn how to compute the sum of square. But before we now learn how to compute the sum of square, we are going to introduce what is called the ANOVA table for the two-way ANOVA, or we call two-way ANOVA table. So you permit me to clean here. We'll be taking it one after the other. After we talk about presentation, we come down to this till we exhaust all of them. So these are the steps that we are going to follow when we want to carry out two-way analysis of variance. We present the data, we calculate the sum of square, we determine the degrees of freedom, we calculate the mean square, we compute the F ratio. We now compare the F ratio which we computed with the F ratio which is tabulated in the what in the textbooks, or tabulated in what in the tables. The first one is the presentation of the data. How do we present our data for two-way analysis of variance? Bearing in mind that there are two factors now in our two-way ANOVA. See how we make the presentation. You can decide to come here and call here your factor A. Here is your factor A. Factor A. And then you can decide to call here your factor B. Here is your factor B. Factor B. So there are two factors here, factor A and factor B. Let us even assume that this factor A might be talking about what of the drug, where the drug has different levels. This time around, let us say there are A different levels of what of the factor. So we now have here to be I. Have here to be I. I will be running from what? From 1, from 2, from 3, down to what? To A. That is to say, this is the first level of this factor A, which could be Fensic. Second level, which could be what? Panadol. Third level, which could be Panadol Extra. Fourth level, which could be paracetamol, down to 8th level of the drugs all targeted to cure headache. Let us equally call this thing factor, talking about the amount of what? Of rest. So I'm going to have here to be J, where J is going to run from what? From 1. Here becomes what? 2. Here becomes 3. Down to what? To B. Where this first level might be talking about 1 hour rest in a day. This second level might be talking about 2 hours rest in a day, 3 hours rest in a day, down to B hours or B hour rest in what? In a day. So the observations I'm going to have in between here are what we call the data for the two-way ANOVA. Okay? Let us say that the recovery time for the first patient here is written as Y subscript 1, 1. 1, 1 here means the recovery time of a person that took the first level of factor A and had 1 hour rest in a day. So here becomes what we call Y12. We talk about the second person that took the first level of what? Of factor A, and then had 2 hours rest what? In a day. Here we have what we call y13 down to what we call y1b. Then we come to the second level. For people taking the second level of what? Of factor A, we have y1, y21. That is the person that received the second factor of level A but had 1 hour rest in what? In a day. Here becomes y22, y23 down to y2b. The same thing applies here. Y31, y32, y33 down to y3b. Here down to ya1, ya2, ya3 down to yab. So we have dot 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 here, dot dot, and then we have dot dot here. This is actually how the two-way ANOVA data layout appears to be. So the observations we have here could be termed the recovery time of the patients that receive this level of factor A and this level of factor what? B. We might be interested now to compute the mean of this first level, compute the mean of this second level, compute the mean of this third level, compute the mean of this 8th level. And at the end, we compare these means to see if any of them is statistically significantly different from the rest of them. What we do is this. We have a line here, then we have a line here. We equally have a line here. I will come here and I will write what? Y dots. And I will explain. In ANOVA, when we make use of dots, we are saying that we have summed observation over a range. That's what we mean by that dot here. So if you come here and you say y11 plus y12 plus y13 down to plus y1b, one thing is constant here, the other is changing. We use a dot to represent that we have summed these observations over that parameter that is changing. And the parameter that is changing is, here is 1 for the column. The first one stands for the row, the second one stands for the column. The row here is 1, the row here still remains 1, the row here still remains 1 down the line. But one thing is changing, the column is changing. So I can come here and say yi dots or y1 dots, showing that I have summed the first level of factor A over the levels of factor B. The same thing applies here, y2 dots, y3 dots, down to ya dots. We can equally sum these observations here to determine its mean, sum this observation, determine its mean, sum this observation, determines its mean. On that note, I am going to have something like this, and I will call here my y dot j. Because if you come here, if you are summing this observation, you find out that the columns are now constant, while the rows are now changing. So you use dots to represent that which is changing. So here becomes y dot 1, here is what? Y dot 2, here is y dot 3, down to y dot b. Okay? Y dot b. We might also be interested to come here and say, let us now sum these observations now, because for us to get the sum of all the observations, It's the same thing like we summing these ones which we have summed out here. And when you are summing these ones here now, what we are now doing is the rows will now be changing here. And we use dots to represent that which is changing. What is constant here is the dot. So we have here to be what? Y dot dot. This Y1 dot here is what we call we have summed, or what we call the level totals. This Y1 dot stands for the totals or the sum for the first level of factor A. This Y2 dot stands for what? The sum or the total for the second level of factor A. But this Y dot dot stands for the sum of all of them, and that's the reason why they normally call it the grand total. The grand what? Total. These are what we call the group totals or level totals. These are what we call the group totals or what we call the level totals. But we call this one the grand totals. So these are the group totals for the different levels of factor A. These are the group totals for the different levels of factor what? Factor B. Why this one is what we call the grand total. If you want to get the mean of this one, what we are going to do is to extend this and have another column. And you'll have what we call yi dot bar. This time around, you are now considering the mean. When you sum, you divide it with the total, which is b, because you sum this over b. So here becomes that y1 dot bar is given as y1 dot all over b, this b here. That y2 dot bar is given as y2 dot all over b. And y3 dot bar is equal to y3 dot all over b. Down that ya dot bar is given as what? Ya dot all over b. Over to this one again, you are going to extend this in this way. And then you have that y dot j bar here becomes what? That y dot 1 bar is equal to what? Y dot 1 all over. You summed over A. So here becomes all over A. Here is that y dot 2 bar is equal to y dot 2 all over what? A. Here becomes that y dot 3 bar is equal to what? Y dot 3 all over what? A. Till you arrive at the dth one. And if you want to get the mean of the grand total, you say y dot dot bar is equals y dot dot all over what? AB. You are saying AB because this y dot dot stands for summing over A and summing over what? Over B. That's what this thing means. So if they ask you to present the layout for this, this is what you do. So permit me to quickly clean this and talk about the one-way and over, the two-way and over table. So I will clean this and talk about the two-way and over table, which of course will make us now to determine the sum of squares. The sum of squares. Okay. If you want to talk about the ANOVA table of ANOVA table, for two-way ANOVA, okay, you are going to put it this way. You have what we call source. S dot V here stands for source of variation. DF here stands for degrees of freedom. SS here stands for what we call sum of SS stands for what we call sum of square. MS now stands for what we call the mean square. And F ratio is now becomes the last one. F ratio. So you now do this way. You do this way. You now talk about what are the source of variation. The source of variations here is a variation coming from factor A. So we have what we call factor A. Factor A. Another source of variation is what we call factor B. Factor B. This time around, we are not talking about interaction. We want to talk about the two-way without interaction. So we now talk about the error, talk about the error term. Then we now talk about the total. Talk about the total. These are what we call the source of variations. So the degree of freedom for factor A is always what? A minus 1. That is the number of levels of factor A minus 1. The same thing applies here. It is what? B minus 1. That is the number of levels of factor B minus 1. The error is A minus 1 into what? B minus 1. While the total is what we call AB minus 1. So this is how to determine the degrees of freedom. So if there are 4 levels of factor A, it becomes 4 minus 1 to here to be 3. If there are 7 levels of factor B, it becomes 7 minus 1 to give us 6. Here is now going to be 4 minus 1, which is 3. This is now 7 minus 1, which is what? 6. It becomes 3 times 6 to give us 18. This one becomes AB, that is 4 times 7 minus what? 1. That's what we call the degrees of freedom. Then when we come to sum of square is now actually going to be sum of square for factor A, sum of square for factor B. So we have what we call S what? A. We are referring to sum of square for factor A. We have S what? B, sum of square for factor B. We have S what? E, sum of square for what? For error. And we have what we call S what? T, sum of square for total. Then when we talk about MS error, we are talking about sum of square divided by degree of freedom. So for me to get the mean square for factor A, the MS for factor A here is going to be SS what? A all over A minus 1. That is, sum of square for factor A all over degree of freedom of factor A will give me mean square for factor A. This one equally becomes what? SS what? B all over what? B minus 1. Here becomes what? SS what? E all over what? A minus 1 into what? B minus 1. We don't have sum of square total. We don't have, mean square total. The only thing we have is sum of square total. Then for us to get our F ratio is going to be mean square of what? Of a factor A all over what? Mean square for what? For error. So here I have what we call MS what? A all over MS error. Here becomes what? MS what? B all over MS what? Error. So for us to be able to get our F ratio, which is our F calculated, we are going to get it for factor A, we are going to get it for factor B. How to get it for factor A is to say sum of square for factor A, mean square for factor A divided by mean square for what? For error. To get it for B, mean square for factor B all over mean square for what? For error. That will give you that immediately. So this is what we call the ANOVA table. Our concern is, what is the relationship that exists between the degree of freedom and then the sum of square? It is important for us to note that here is what we call the degree of freedom for total. That our DFT, please, we mean degree of freedom of total here, is equal to DF of A plus DF of what? Of B plus what? DF of what? Of E. What we mean here is that the degree of freedom for total is equals to the degree of freedom of what? Of factor A plus degree of freedom of factor B plus degree of freedom of what? Of error. And you and I know that degree of freedom for total is AB minus A. Therefore, our AB minus 1 equals to degree of freedom for factor A is what? A minus 1 plus. That of factor B is what? B minus 1 plus. That of error is A minus 1 into B minus 1. This is the relationship that we have to bear in mind. The same thing applies for sum of what? Square. Sum of square of total is equals to sum of square of factor A plus sum of square of factor B plus sum of square of what? Of error. So there could be a scenario where you might be given this in an exam, you might be given this, you might be given this, and you are required to find this. You use this relationship to do that. Okay? Or you might be given this, you'll be asked to find this. You use this relationship to find it. So a lot of things can be asked you about this ANOVA table. So another thing we are going to consider is, what is the formula for sum of square total? What is the formula for sum of square A? What is the formula for sum of square B and that of error? We are going to quickly show that so that we can conclude what we are doing to manage the size of this video. So permit me to clean this and then give us the formula for sum of square total, sum of square A factor A, sum of square factor B, and sum of square error. Because we getting this and knowing the degree of freedom, we can find everything here. So permit me to clean this one.